Edexcel Core Pure, Matrices 2, Transformations and Invariants. We're going to be looking at invariant lines and invariant points. In previous sessions we've been looking at how matrix transformations can transform an object to an image. And now we're going to look at individual points to see what the matrix might do to that point. To start off with, I'm going to consider the matrix 5, 4, 2, 3, and I'm going to take an object with coordinates 1, 2. So that's my object. And when I multiply the matrix by that point 1, 2, we'll create an image. So here we have 5 times the 1 and 4 times the 2 to get 13. And then we've got 2 times the 1 and 3 times the 2 to get 8. So that image is the point P dashed, and we can see that P and P dashed are clearly in different places. The object P has moved to a different location called P dashed. However, if a particular point is invariant, then it does not move under the matrix transformation, and P dashed will be identical. For example, if I take the same matrix 5, 4, 2, 3 and apply it to a different point, this time we're going to apply it to 2 minus 2. So there's my object P, and let's see where the image is. So we've got 5 times 2 and 4 times minus 2 is 10 take away 8, which is 2. And then we've got 2 times 2 and 3 times minus 2 is 4 take away 6 is minus 2, which is P dashed. So we can see here that the point P has not moved under the matrix 5, 4, 2, 3. Therefore the point P must be an invariant point under this matrix transformation. So now we're going to look at how can we find invariant points. Before we look at how we find invariant points, there's a simple but important question to consider. What happens to the origin under a matrix transformation? So if I take the matrix 5, 4, 2, 3 and apply it to the origin, we can quickly see we get 5 nothing add 4 nothings, we get 2 nothings add 3 nothings. So the origin is itself an invariant point. So if the origin was the object, the image of the origin would be in the same place. So the origin is an invariant point. So we need to generalize this idea now and see if we can find some more invariant points. So I'm going to take my matrix 5, 4, 2, 3 and I'm going to apply it to a general point xy. So my object is xy. If we're looking for invariant points, then the image will also need to be called xy. So the object and the image must be in the same place. So if I do the multiplication on the left, we get 5 times x and 4 times y, 2 times x and 3 times y, and it needs to be in the same place as xy. Okay. If we have equal matrices, we've seen previously that the corresponding elements must match. So if we look at the top elements first, we've got 5x plus 4y is x. In other words, with a little bit of rearranging, 4x plus 4y is 0. And if we look at the bottom elements, 2x plus 3y needs to be y, and again a little bit of rearranging, we get 2x plus 2y is 0. If you look at the top equation, if we divide by 4 we get x plus y is 0, and if you look at this bottom equation, if we divide by 2 we get x plus y is 0. So both equations are consistent, and they are both consistent with the line y equals minus x. So that line is a line of invariant points. Every single point on that line will be unaffected by the transformation 5, 4, 2, 3. So looking at the matrix 5, 4, 2, 3, we've found the line of invariant points, which is the equation y equals minus x. So what does that represent geometrically? It means that if we take any point on that blue line and apply the matrix 5, 4, 2, 3, it will remain in exactly the same position. So here we have the matrix M, 5, 4, 2, 3, and we are going to apply it to the object line, which is y equals minus 2x. We have a point P on the object line, which is currently at 1 minus 2, and the image is P dashed. We can see the red object line is being transformed into the green image line by the matrix at the moment. But if I start to change the gradient of the red object line, we can start to make them match up. Okay, and in fact, if I get to y equals minus x, there's a perfect match. You can see the object and the image are in the same place. If I start to change the equation of this line by controlling the plus c at the end of the line, so c0, we can see the object and the image move apart. So the only line of invariant points is y equals minus x. So we've looked at a line of invariant points, but what about an invariant line? An invariant line is mapped onto itself by a transformation. Really important to note that individual points on that line may not map onto themselves exactly. So the object on the line may move to a different location on the same line. So what lines would we expect to be invariant in the reflection y equals x? Which lines would be invariant lines under that transformation, reflecting the y equals x? So here we have our reflection matrix M, 0, 1, 1, 0. Our current object line is the red one, and the image is the green one. We've got a point P, which is on the object line, and a point P dashed on the image line. So I'm going to see if I can make these lines coincide with each other. And they coincide when we get to y equals minus x plus 4. Notice P and P dashed are not in the same location. So P is not an invariant point, but y equals minus x plus 4 is an invariant line. If I now start changing C, we get a whole series of invariant lines. So every line of the form y equals minus x plus c is an invariant line under the reflection matrix 0, 1, 1, 0. So an invariant line is mapped onto itself by a transformation, but it's important to know that individual points on the line may not map onto themselves under that transformation. So what lines would we expect to be invariant in the reflection in the line y equals x? So we've seen geometrically that the invariant lines have the form y equals minus x plus c, but you can see on integral for notes on finding invariant lines algebraically.